2.5, rational functions. So a rational function is just going to be a function where the numerator and the denominator are polynomials. So something like 2x plus 1, that's a polynomial, over x squared minus 5, that's a polynomial. So if it's a polynomial over polynomial, this whole thing altogether, oops, that's not my pointer, this whole thing altogether is a rational function. Something like 1 over x plus 2, that's a rational function. So rational functions, numerator and denominator, are both polynomials. We're going to talk about a few things, mostly graphing them. So we're going to talk about some stuff that leads up to graphing, and then we'll talk about graphing rational functions. So the first thing we're going to talk about are asymptotes. Now, first, if you haven't heard me make this rant in class, you're going to hear it now. If you've already heard it, you're hearing it again. The word is asymptote. That is a T right in there. For whatever reason, many people, including mathematicians with PhDs, say the word asymptote as if there were a P there. But there's no P there. It is just, it's a T. It's asymptote. Now, I think people say that because it sounds like isotope. Is it really important right now? No. Does it make me cringe when I hear it? Yes. So I'm going to make that rant that it is the word asymptote, not the word asymptope. All right? Tote, not tope. All right. Getting off my high horse, stepping down. Let's talk about asymptotes. So 2 types of asymptotes that we're going to talk about. There is a third type, but we're just going to ignore it. And you may run into it in calculus, but your teacher will explain it again then if they need you to know it. So first of all, we have vertical asymptotes, which I'm going to label VA because that is a lot faster to write than vertical asymptote. And vertical asymptotes are going to happen where the denominator equals 0. So it's an up and down line. And up and down lines are going to be of the form x equals a number. So we're looking for, here's my pointer, we're looking for the x values that make the denominator of a rational function 0. That's where you're going to get these up and down lines. So the way asymptotes work is that the graph is going to get really close to it, but it's not going to actually touch it. It's just going to kind of go up forever and hug it on its way up or on its way down. So on this side over here, you can see that it's hugging it all the way down. So your graph is never going to, if I make just a really bad sketch here, your rational function is never going to just kind of ignore the vertical asymptote. That won't happen. It always has to either hug it on the way up or hug it on the way down. Let me just erase that. For horizontal asymptotes, these are horizontal lines. Horizontal lines are going to be of the form y equals a number. And horizontal asymptotes are a little bit more tricky. With the vertical asymptotes, you just solve where the denominator equals 0. With horizontal asymptotes, there are rules. And in calculus, you'll actually get into why these rules exist. But for this course, they're just going to be rules that I tell you and you're going to have to accept unless you want to go on a little adventure and look up online why, the calculus reason why horizontal asymptotes have the rules they do. So you're more than welcome to do that. We're just not doing it in this video. So it all depends on the degree of your numerator versus the degree of the denominator. So if I go back here and look at this guy here, the degree of the numerator, that's the highest degree on x, the highest power on x, and the highest power on x is 1. So the degree of the numerator is 1. The degree of the denominator is 2 because the highest power on x is a 2. For this guy over here, there's no x in the numerator, so the degree of the numerator is 0. And in the denominator, the highest power on x is just a 1. So the degree of the denominator is 1. So in both of these cases here, the degree of the numerator is less than the degree of the denominator. But you could have situations where the degree of the numerator is greater than the degree of the denominator, or they could be the same degree, and we have rules for each of them. In the case that the degree of the numerator is greater than the degree of the denominator, there's not going to be any horizontal asymptote. And I'm abbreviating that HA. If the degree of the numerator is equal to the degree of the denominator, Then you're going to have a horizontal asymptote at y equals, and this one's a little weird, ratio of the leading coefficients. And I'll explain a bit more. Ooh. Squeezing it all in there. Ratio of the leading coefficients. So if I kind of scroll down a little bit, and because we're on a computer, we can do some fancy manipulation. Isn't that fancy? Can't do that in a classroom. All right, so as an example, if I had 2x squared plus 5x minus 1 all over 3x squared minus 7, the degree of the numerator and the degree of the denominator are the same. So the degree of the numerator is 2 because that's the highest power. And the degree of the denominator is also 2. So these are the same. When we say the ratio of the leading coefficients, ratio typically means fraction, and it is going to end up being a fraction. So you just take the leading term on the top, so that's the term with the highest power of x, so in this case 2x squared. You're taking his coefficient and you're putting it over the leading coefficient for the bottom, so whatever the coefficient on the highest powered term of x is for the denominator. So for this guy here, there will be a horizontal asymptote at y equals 2/3. And my computer just beeped, ignore that. I'm gonna go ahead and mute that. There we go. So if the degree of the numerator is equal to the degree of denominator, that's when it's y equals a ratio of the leading coefficients for your horizontal asymptote. Finally, if your degree of your numerator is less than the degree of your denominator, you're going to have a horizontal asymptote, and it's at y equals 0. So those are the 3 different situations you can run into. With horizontal asymptotes, pictorially, graphically, if you will, they're also going to hug the asymptote. They can hug it from the top or the bottom. Now, it is okay to cross a horizontal asymptote. So I could draw a picture here. I'll just put I'll put a vertical in there, and maybe I'll put 2 verticals and a horizontal for funsies. What you're going to notice is that they're always going to hug the asymptote on the way out. So notice that when I go out this way, it's getting really close to that horizontal asymptote, but not touching it. Same with the vertical, it's getting really close. But it would be totally fine if I had on the inside something like this. It's okay to cross. So it crossed the horizontal asymptote. That's okay. You can't cross vertical asymptotes with rational functions. You cannot cross the vertical asymptotes. But you can totally cross horizontals. That's fine. Horizontals just tell you that in the long term, the function is going to even out to that number. So let's go ahead and do a few examples. Let's start with just finding vertical and horizontal asymptotes. So here we have the function f of x equals 9x minus 5 over negative 3x plus 3. For the vertical asymptotes, that's where you're setting the denominator equal to 0. And then you're solving for x. So the denominator here, that's this negative 3x plus 3 equals 0. Subtracting the 3, we get negative 3x equals negative 3. And then if we divide both sides by negative 3, we'll get x equal to 1. So there's a vertical asymptote at x equals 1. Now, it's really important that you know that asymptotes are equations of lines, which means that the x equal part is important. You can't just say the vertical asymptote is at 1. The vertical asymptote is at x equals 1, because that's part of the equation of the asymptote. All right. For the horizontal asymptote, we're comparing the degree of the numerator to the degree of the denominator. the highest powered term in the numerator is just x raised to the first power. So the degree of the numerator is 1. And the degree of the denominator is also 1. That's the highest power of x that you see. So the degree of the numerator is equal to the degree of the denominator. Which means there's a horizontal asymptote. If we come back here, there's a horizontal asymptote at y equals a ratio of the leading coefficients. All right, so if I just go ahead and rewrite my function, f of x equals 9x minus 5 all over negative 3x plus 3. The leading coefficient on the top is 9. The leading coefficient on the bottom is negative 3. So there is a horizontal asymptote at y equals 9 over negative 3, and that simplifies to just negative 3. So I could just erase this and put negative 3. There is a horizontal asymptote at y equals negative 3. So let's do another one. Again, we're finding horizontal and vertical asymptotes. So for the vertical asymptote, we're setting the denominator equal to 0. Ooh, my handwriting's awful there. All right, so the denominator is negative x plus 4 equal to 0. Subtract the 4 off both sides, you get negative x equals negative 4, and then multiply or divide both sides by negative 1, and you'll get x equals 4. So there is a vertical asymptote at x equals 4. For the horizontal asymptote, the degree of the numerator, because there's no x's, is going to be 0. So the degree of the numerator is 0. And then the degree of the denominator, because there's a power of x, the first power of x, the degree of the denominator is 1. So that means that the degree of the numerator is less than the degree of the denominator. If we go back to our handy-dandy cheat sheet, if the degree of the numerator is less than the degree of the denominator, there's a horizontal asymptote at y equals 0. And that's that. So one last one where we find just the vertical and horizontal asymptotes, and then we're going to talk about graphing. Here we have f of x equals 5x cubed minus 1 all over x squared minus 9. Vertical asymptote, once again, set the denom equal to 0 and solve for x. So we have x squared minus 9 equals 0. I'm going to factor that because it's a difference of squares. So we have x plus 3 times x minus 3 equal to 0. This gives me x equal to negative 3 and x equal to positive 3. So there are vertical asymptotes at x equals negative 3 and x equals positive 3. So sometimes you might have to factor the denominator in order to find those asymptotes. For the horizontal asymptote, so the degree of the numerator, the highest power is 3. The highest power in x is 3. So the degree of the numerator is 3. The degree of the denominator is 2. That means that the degree of the numerator is greater than the degree of the denominator. If the degree of the numerator is greater than the degree of the denominator, let's get back to this page, there's no horizontal asymptote. So degree of numerator greater than degree of denominator, no horizontal asymptote. and that's the answer there. So this was just finding the vertical and horizontal asymptotes. Let's talk about what to do with that information and how to turn it into a graph. That'll be our next step. So the way that Alex is going to ask you to do these types of problems is going to be a little bit different. They're not going to ask you to make a sign chart. The wording on theirs, it's actually just going to ask you to match a function to a graph, but I want to show you the full process, including finding asymptotes and intercepts and making a sign chart and using that all to sketch the graph of our function. So we have g of x equals 2x minus 2 over x squared minus 3x minus 4. We're going to start with the asymptotes. So with the vertical asymptotes, we're looking at the denominator being set equal to 0. This is a quadratic and I can factor it, so this will be x minus 4 times x plus 1 equal to 0. So I have a vertical asymptote at x equals 4 and at x equals negative 1. For the horizontal asymptote, the degree of the numerator is 1. The degree of the denominator is 2. So the degree of the numerator is less than the degree of the denominator. Which means that there's going to be a horizontal asymptote at y equals 0. So we have the asymptotes. Let's talk about intercepts. Let me make it a fun new color. Let's do teal. All right, so for the intercepts, for the x-intercept, this is where you let y equal 0. In the case of function notation, we just pretend g of x is the y. So you'd get 0 equals 2x minus 2 all over x squared minus 3x minus 4. Now, here's the thing. The only way that a fraction can be 0 is if you have 0 over a number. There's no other way for a fraction to be 0. Even 0 over 0 doesn't work because that's not actually a number. And a number over 0 won't work either because that's undefined. So the only way that this whole thing here can be 0 is if the numerator is 0. So all you really need to do is set the numerator equal to 0 to find the x-intercepts. So the numerator is 2x minus 2 equal to 0. 2x is equal to 2. X is equal to 1. So there is an x-intercept at the point 1, 0. Right. For a y-intercept, we're looking at plugging in x equals 0. So we have y equals 2 times 0 minus 2 all over 0 squared minus 3 times 0 minus 4. So most things just kind of go to 0, but at the top we have negative 2 over negative 4, which simplifies to 1/2. So there's a y-intercept at 0, 1/2. And let me circle all the relevant information right now. So we have vertical asymptotes, we have a horizontal asymptote, an x-intercept, a y-intercept. You could have multiple x-intercepts, by the way. You're only going to have one y-intercept if you have a y-intercept, but you could have multiple x-intercepts. And then the next thing it says is to make a sign chart and use the information to sketch a graph of the function. So see if we have enough room on here. No, I think I'm going to copy this information over to another slide. Hold on, I'm going to pause the video, copy it to another slide so we have a little bit more room to work with. All right, so I've copied down the information over here that we had from the previous slide, and then I have our function here. So the next step is making a sign chart. And to make a sign chart, you need to factor the numerator and the denominator. So I'm going to go ahead and do that. On the top, actually let's do it in blue. On the top, I can pull out a 2, and then I'll have x minus 1. On the bottom, we've already factored this. It's x minus 4 times x plus 1. And then we find the places where the numerator and denominator would be 0. So here you get x equal to 1, x equal to 4, and x equal to negative 1. Make yourself a beautiful sign chart. And put your zeros down in order. So negative 1, 1, 4. Choosing some test points. I'll do negative 2, 0, 2, and 5. And then remember, you're taking the test points and plugging them in for each factor here. Now, this 2 right here doesn't really matter because every time we would plug in, the 2 is going to stay positive. So I'm just going to kind of ignore that the 2's there. I'm just going to plug into this factor, and this factor. Now, if this were a negative 2, you would need to put a negative in front each time because there would be a negative 2 there. But that's not the case. Oops. So let me erase those. All right, so negative 2 minus 1 is negative, over negative 2 minus 4 is negative, negative 2 plus 1 is negative. 3 negatives are going to make a negative. When you plug in 0, 0 minus 1 is negative, 0 minus 4 is negative, 0 plus 1 is positive. So 2 negatives make a positive. When you plug in 2, 2 minus 1 is positive, 2 minus 4 is negative, 2 plus 1 is positive, 1 negative makes a negative, 5 minus 1 is positive, 5 minus 4 is positive, 5 plus 1 is positive. All positives make a positive. What we're going to do now, remember back to when I talked about nonlinear inequalities, we said that the positives related to being above the x-axis and the negatives were below, where the function was below the x-axis. So these negatives here mean below x-axis. And the, oops, I wanted to use a different color, green. The positives are where the function is above the x-axis. All right. So, with all this information, I'm going to go grab a graph from online and place it in here. So I'm going to pause it again, put a graph in here so I don't have to hand sketch a graph. If we're using technology, we might as well use it the right way. So hold on just a sec. Well, you won't have to hold on at all, but it'll be here right about now. All right, so I grabbed a graph and I also have rearranged things a little. Okay, we're going to start by plotting the things we know. So for instance, we know that there's a vertical asymptote at 4 and negative 1. So at negative 1 is right here. It's a vertical asymptote. This is going to be, I'm labeling it x equals negative 1. I don't like how that middle portion looked extra solid. Make sure it looks like a dashed line. This will be x equals 4. There's a horizontal asymptote at y equals 0, which is just the x-axis. And then I'm going to label our points here. So we have the point 1, 0, That's right here. And then 0, 1/2, which is like right here. And then we have this information. So really, it's like our graph is being split up into 4 different sections. There's the section that happens before -1. There's the section between -1 and +1, between +1 and 4, and then after 4. And these are just telling us if it's below or above the x-axis. And believe it or not, that's enough information for us to know what it looks like. So for everything less than -1, so for this whole section here, it needs to be below the x-axis. So my choices are between here. So basically here are the 2 different things that could happen. Either it's going to make this shape or it can make this shape. There's no other choice of shapes it can make. One of these is below the x-axis, and it's this guy here. So let me undo that part. So in order to be below the x-axis, he would be right here. For this portion between -1 and 1, it says it's above the x-axis. So the choices that you're making is it's either going to come up from this way or it's coming up from this way. The only options here are that it comes from one of these ends. It has to hug the vertical asymptote either here or here. Since it says above the x-axis, this part right here wouldn't make sense. So it has to come from up here, and then it goes down and it has to touch every point. Let me undo more than that actually. So I have to touch the y-intercept right here. So I'm going to just be very careful. Beautiful. So I'm touching that and I'm coming down here and I'm touching the other point. That's our x-intercept. So make sure you touch all the points that you've plotted. And then it says below the x-axis. So my choices right now, this could bounce all the way up like this, or it could go down like this. If we were above the x-axis, if this were a positive, we would choose this guy. But because it's negative, it says it's below the x-axis between 1 and 4, we're going to choose this one. So it'll look a little like this. For the last section, we have choices. It's either going to be this guy or it's going to be this guy. So it's always going to hug the asymptotes. We say it says it's above the x-axis, which means that we should choose this shape right here. See if I can just erase that. Beautiful. And that's our graph. There it is. So yeah, it's a bit of a process, but if you just follow it through, it works. So let's do another example. All right, same question. Here our function is h of x equals 6 over x squared minus 2x minus 8. We'll start with the vertical asymptotes and the horizontal asymptote. So for vertical asymptotes, we're looking at where the denominator equals 0. So x squared minus 2x minus 8 equals 0. This factors into x minus 4 times x plus 2 equal to 0. So we get x equal to 4 once again, and then x equal to negative 2. For the horizontal asymptote, the degree of our numerator is 0. And the degree of our denominator is not 1, it's 2. So 0, 0 for the numerator, 2 for the denominator. So the degree of the numerator is once again less than the degree of the denominator. So there's a horizontal asymptote at y equals 0. Let's talk intercepts. For the x-intercept, this is where you were letting the numerator equal 0. But if you set the numerator here equal to 0, you get 6 equal to 0, which doesn't make any sense at all, so there's no x-intercepts here. for the y-intercept, you're plugging in x equals 0. So you'll have y equals 6 over 0 squared minus 2 times 0 minus 8. So 6 over negative 8, which is going to give you negative 3/4 or negative 0.75. Hopefully, yes. So negative 0.75. So your y-intercept is 0, comma, negative 0.75. Right. Once again, I'm going to take this information, copy it to the next page, and put a graph in and make it so we can look all beautiful. So hold on. All right, so here we have all our information. We are once again going to make a sign chart. So we'll start by factoring, which we've already really done because this was x minus 4 times x plus 2. If you try to set the numerator equal to 0, you're not going to get anything. So there's nothing from the numerator. You just have x equals 4 and x equals negative 2 for your sign chart. So we have negative 2, 4. So here we have negative 2 and 4. We're making a sign chart. So I'll choose test points, negative 3, 0, and 5. Now, when I plug it into this, the numerator is always going to be positive because 6 is a positive number always. So I'm just going to come in here and put a positive in the numerator to begin with because we know the numerator is always going to be positive. Then plugging into the bottom two. So negative 3 minus 4 is negative. Negative 3 plus 2 is negative. Two negatives make a positive. 0 minus 4 is negative. 0 plus 2 is positive. One negative makes a negative. 5 minus 4 is positive. 5 plus 2 is positive. All positives make a positive. So negatives are going to be below the x-axis. And positives are going to be above the x-axis. So let's come to our graph and let's draw in the asymptotes and the intercepts and start there. So vertical asymptotes at 4 and negative 2. So here's one at 4. Here's one at negative 2. There's a horizontal or a vertical asymptote. A horizontal asymptote at y equals 0. And the nice thing here is that the way that our sign chart is chunked is actually the same as our graph is chunked up. So it's telling us a lot of information. Let me also, I forgot to, there you go, plot the y-intercept of 0, negative 0.75. All right, so between negative infinity and negative 2, which is this portion here, we are above the x-axis. So our choices were either it makes this shape or it makes this shape. So if it's above the x-axis, it has to be this guy up here. Okay. And then between negative 2 and 4, so this whole area, it's below the x-axis the entire time, which means it never touches the x-axis. It can't, it's below it the entire time. So you know, choices on how you do it. I mean, we're not graphing calculators. We can't be perfect. You make the best choice you can, the best drawing you can. I guess really Alex will be doing it for you, but please do them on paper, you know. Exercise those skills. All right, finally, between 4 and infinity, we are above the x-axis again, so hugging the asymptotes in both directions. There we go. Beautiful, wonderful graph. And that's that for this problem. All right, so here's the last problem we're going to do. Same question as before. we're finding everything and using it to graph. We have h of x equals 2x squared minus 2 over x squared plus x minus 6. We'll start with the vertical asymptotes. So letting the denominator equal 0 and finding out what x values make it 0. This factors into x plus 3 times x minus 2. So we'll get a vertical asymptote at negative 3 and positive 2. For the horizontal asymptote, the degree of our numerator is 2. The degree of our denominator is also 2. So the degree of our numerator is equal to the degree of our denominator. Which means that, let me scroll back to our list so you can look at it. It means we're in this ratio of the leading coefficients territory. So we're just taking that coefficient of the leading term on top over the coefficient of the leading term on bottom. So for us, there's like secretly a 1 right here. So it's 2 over 1. Over 1, which is just the same as 2. So there's a horizontal asymptote at y equals 2. For the intercepts, for the x-intercept, that's where you let the numerator equal 0. So 2x squared minus 2 equals 0. Factor out a 2. X squared minus 1 equals 0. This is a difference of squares, and it factors into x plus 1 times x minus 1 equal to 0. So we'll get negative 1 and positive 1 as our x-intercepts. For the y-intercept, we're going to let x equal 0. So we have 2 times, this is y equals, 2 times 0 squared minus 2 over 0 squared plus 0 minus 6. So negative 2 over negative 6, which is 1/3. So 0, 1/3. Once again, I'm going to copy this all down onto the next slide and put a graph in. All right, so here's everything. Since we had already factored this on the previous page, we factored the numerator here and we factored the denominator here. I went ahead and just wrote it in its factored form. And then this is all the information from the previous page. The vertical asymptotes, horizontal asymptotes, x-intercepts, y-intercepts. We need to make a sign chart still. So we, just like we would with nonlinear inequalities, finding where the zeros of the polynomial on top and the polynomial on bottom are. So we get x equal to negative 1, x equal to 1, x equal to 2, and x equal to negative 3. So let's see, negative 3, negative 1, 1, and 2 for test points. I'll do negative 4, negative 2, 0. There's not really good choice here, so I'm just going to choose 1.5, and then 3. Because this 2 doesn't matter, this 2 is always just going to be a positive 2, I'm just going to look at these 4. So negative 4 plus 1 is negative. Negative 4 minus 1 is negative. Negative 4 plus 3 is negative. Negative 4 minus 2 is negative. 4 negatives make a positive. Negative 2 plus 1 is negative. Negative 2 minus 1 is negative. Negative 2 plus 3 is positive. Negative 2 minus 2 is negative. 3 negatives make it negative. Plugging in 0, 0 plus 1 is positive. 0 minus 1 is negative. 0 plus 3 is positive. 0 minus 2 is negative. 2 negatives make a positive. Plugging in 1.5. 1.5 plus 1 is positive. 1.5 minus 1 is positive. 1.5 plus 3 is positive, but 1.5 minus 2 is going to be negative. Sorry, 1.5 minus 2 is negative. One negative makes a negative. And then when you plug in 3, 3 plus 1 is positive, 3 minus 1 is positive, 3 plus 3 is positive, 3 minus 2 is positive. All positives make a positive. The negatives are where the graph is going to be below the x-axis. And then the positives are where the graph is going to be above the x-axis. So on my graph, I'm going to start by graphing the asymptotes and intercepts, and then I'm going to use my entire beautiful sign chart to graph the most beautiful graph we've ever seen. So we'll start with -3. We have a vertical asymptote at -3. Then we have another one at +2. There is a horizontal asymptote at y = 2. X-intercept at -1 and +1. And then a y-intercept at 1/3. So, I mean, mine's going to kind of look more like 1/2, but, you know, use your imagination. All right, so when we're making choices on this first section here, the choices are either it looks like this or it looks like this. Those are the two choices. Either way, it has to hug the asymptote, the horizontal asymptote, and it has to hug the vertical asymptote. So if we're above the x-axis, between these two choices, this is the one that's above. So we will draw in there. Now, between -3 and -1, the reason that it stops at -1 is because you can even kind of see what's happening here between -3 and 2. So this whole section is this section. You can see what's happening, that it's above the x-axis very briefly between -1 and 1, which is what it says right here. And then after that, it's below the x-axis. So this, based on the 3 dots that we drew, it almost makes it obvious where the graph, what shape the graph is going to be in. It kind of guides you in the right direction. But this here confirms it, that it should be below down here, and then between 1 and 2, so here's 1, here's 2, it should also be below. So we're just going to kind of follow the guidelines. Beautiful. All right. And then after 2, so after 2, it's above the x-axis. So our choices would be either it makes this shape or it makes this shape. The only one that's above the x-axis would be right here. And there is my beautiful, wonderful, gorgeous graph. And that's it for this section. So it is a lot of work on these ones, but I think it's a lot of fun. It's really nice to see the payoff in a beautiful, well-drawn graph, right? Like, look at how beautiful these are. I even drew each of them in different colors for funsies. So I hope you have a fun time drawing some graphs. That's it for rational functions. I will see you in the next video. Bye.